Hey everyone, welcome back. In today's video, I'm going to be going over the top 6 dynamic programming patterns you need to know for coding interviews. These patterns are crucial to understand if you want to develop a higher level understanding of dynamic programming and solve more difficult dynamic programming problems. As you can see on the screen, here is the list that I've compiled for this video. I'm going to be explaining what the pattern is, how they're typically implemented, which I'll explain with an example, and related problems that you can practice on. Alright, without further ado, let's get into it. The first pattern I want to look at are the knapsack type problems. Now, originally I thought about splitting this into 2 parts because there are 2 main types of knapsack problem, those being 0-1 knapsack problems or unbounded knapsack problems. The reason why I chose to just lump them together under one category is because they're both very similar. The only difference between the two is whether items can be selected multiple times or not. In any case, I will still be going over both types so you can have a better understanding of this pattern. The thing that makes knapsack problems unique is that they add a unique state to the problem that most dynamic programming problems typically don't have, and that is the capacity. So let's first take a look at the infamous unbounded knapsack problem. Basically, the way this problem works is we're given a list of items and a capacity. The goal is to maximize the value of items in a knapsack without any limit on the number of times an item can be included. In other words, we can use the same item multiple times in our knapsack, hence the name unbounded. So let's start out by taking a look at a simple example. As you can see, we have a knapsack with a capacity of 5, with 3 possible items to choose from. We have item 1 with a value of 4 and a weight of 2, item 2 with a value of 3 and a weight of 1, and item 3 with a value of 5 and a weight of 3. Using these items, can we fill our knapsack with items up to our capacity to maximize the value? Since we can use the items multiple times, then there are many possible combinations we can choose from to maximize the value in our knapsack. So how can we know for sure we have found the most optimal solution? Well, we can try finding every possible combination to find the max value that way. If we were to draw this out, then we would get a really complicated looking decision tree outlining each choice we can make. We can start with 0 items selected, which would leave us with a starting capacity of 5. If we decide to select, let's say, item 1, then we subtract 2 from 5, because again, the weight of item 1 is 2, so 5 minus 2 leaves us with 3. So if we select item 1, then that'll leave us with a remaining capacity of 3. So now that we have a capacity of 3, we can actually choose to select item 1 again, or we can try item 2 or 3. So now our decision tree splits off in 3 different directions. One branch splits off if we select item 1 again, and then one for item 2, and then one for item 3. And so the remaining weights after all these different branches have been selected. And so if we decide to pursue either of these paths, the remaining weight will be 1, 2, and 0. Because if we select item 1, for example, our remaining capacity here is 3. And so the weight of item 1 is 2, so 3 minus 2 is 1. Similarly for item 2, the weight is 1, so 3 minus 1 is 2, and so on. And for the sake of time, I'm not going to draw out this entire decision tree because it can get pretty big. But if we were to take a step back, if we start out with a capacity of 5, we can also choose to take item 2 first or item 3. So we have item 2 and 3 selected here. And again, that would leave us with a remaining capacity of 4 if we take item 2, or a capacity of 2 if we decide to take item 3. And then these would all split off in their own little subtrees over here, showing the different decisions that we can make by including or excluding certain items from our knapsack. The point that I'm trying to make here is that since we would be exploring every possible combination, we are bound to have repeat work at some point. If you watched the first video in the series, you would know that this is called overlapping subproblems. And these subproblems ultimately add up to the highest value we can put in our knapsack if we allow repeat items. This is known as optimal substructure. This all means we can leverage dynamic programming to help optimize the problem. So now that we have a decision tree, we need to determine the dimensions of our problem so we can use the appropriate data structure. A normal one-dimensional array will not work in our case, because we have 2 variables to track, those being our items and our capacity. We can say that our choices are proportional to the size of the items and capacity we're given. In other words, our dimensions are n times c, with n representing the number of items and c representing our capacity, which means we can leverage a matrix to help solve the problem. Now, I'm going to fast forward a bit here to a finished matrix for the unbounded knapsack problem, where I'll then give a brief rundown of how this problem works. Alright, basically, the way this works is at every coordinate in our matrix, we need to either include or exclude an item at a certain weight capacity to yield the most value. When looking at the first row, we're only considering item 1. Our only constraint here is our capacity. So by the end of the first row, we've determined that when we're at our max capacity of 5, we can store item 1 twice, because item 1 has a weight of 2, for a total value of 8. Moving on to our second row is where things get interesting. Now, we're allowed to either include item 2 or exclude it in favor of the previous item. Basically, since we're allowed to choose the same item multiple times, if we decide to take the item at the current coordinate, then we can look to the left at previous calculations by subtracting the current item's weight from the current capacity. If we decide to take the item at the current coordinate, then we can look to the left at previous calculations by subtracting the current item's weight from the current capacity. An example would be here at this coordinate. If we choose to take item 2 here, then that still leaves us room in our knapsack. This is because item 2 has a weight of 1, and at this point our capacity is 2. So 2 minus 1 is 1. This moves us left to our previous coordinate, with a capacity of 1, where we've already calculated a max value of 3. Then if we were to take item 2 again, then we would end up here, meaning we ran out of space, which means at this coordinate we can choose item 2 twice, or we can exclude item 2 in favor of the previous item, item 1. And we can do this by simply looking up. In this case, at this coordinate, we have a max value of 4. Since 6 is greater than 4, that is why we choose 6 for this coordinate. This is the most amount of value that we can store in our knapsack at this point with a capacity of 2 in our knapsack. Basically, the best choice we can make up to this point is taking item 2 twice. So essentially, the basic movements we can do in our matrix when dealing with an unbounded knapsack problem is to either look left or up. Then after this coordinate, this process repeats for the rest of the matrix, until we reach our final answer of 15. And here's the thing, we can actually trace the decision making like so. Starting from the bottom right, we actually choose to exclude item 3 in favor of item 2. You can tell because the row above also has 15 in it, which means we included item 2. With unbounded knapsack, if you ever see a coordinate with a value above it that is the same, that is basically saying we're excluding the one underneath. And the reason we go left all the way is because all the values calculated in this row are greater than whatever is above it in this row for considering item 1. So we just choose item 2 all the way. And again, when we encounter a coordinate that shares the same value with the coordinate above it, we move up until that changes. But in our case, this leads to the starting point, which ends the decision making. So if you couldn't already tell, the optimal answer to this problem is selecting item 2 5 times. Because item 2 has a value of 3, 3 times 5 equals 15. Overall, this is a pretty high-level overview of how the unbounded knapsack problem works. And if you guys would like, I can make a separate video covering that topic more in depth. Same goes for the 0-1 knapsack problem. Speaking of which, the process is similar to the unbounded knapsack, but instead of looking left in the same row, we have to look diagonally because we can't use the same item more than once. Once we decide to exclude an item, we have to look at the previous item. So let me redraw this matrix showing how the problem would look if we were dealing with an 0-1 knapsack instead. So this is how the matrix looks when solving our problem following the 0-1 knapsack constraints. I won't go through the problem step by step, but I can give a basic rundown of how we can make decisions in a 0-1 knapsack matrix. So if we look at the bottom right of our matrix, we have our final answer of 9. But how do we calculate this? Well, if we decide to include item 3, then we can get a value of 5 and a weight of 3. Taking our current capacity of 5, we can subtract the weight of our item, which is again 3. 5 minus 3 is 2. And because we can't use the same item twice, we have to look at our previous row at item 2. So now we look at this coordinate. Since it's the max value calculated for this item with a max capacity of 2. Remember, 5 minus 3 is 2, which is why we are looking here. And since we have space to accommodate item 2 in our knapsack, we can take it and add it to our total. So the 5 from item 3 and the 4 as calculated here, 5 plus 4 gives us a total of 9. Now after adding item 3 and 2, we actually still have a capacity of 1 left in our knapsack, but we cannot consider item 1 since it has a weight of 2. So that is why 9 is our final answer. I hope this is all making sense so far. The way we move in either matrix differs based on if we can include multiple of the same item or not. In the 0-1 knapsack problem, we have to move diagonally. Since if we decide to include an item and have space for more, we have to look elsewhere, since we can only have one item of each. Contrast this with the unbound variant, we can use multiple of the same item. This allows us to move left to consider the same item multiple times. And that was basically a high-level overview of the knapsack pattern. Again, if you'd like me to cover these topics more in depth, let me know in the comments below, and I can do that for a future video. In any case, let's move on to the next pattern. Next up are grid-based dynamic programming problems. I know that we just used a grid or matrix for the knapsack problems, but this is different. In the knapsack problems, we were focused on optimizing our selection of items to meet a certain weight capacity. But with grid-based problems, the state is often the grid itself. Some examples of problems that are grid-based are these. We have unique paths, minimum path sum, and maximal square, to name a few. Basically, grid-based DP problems are more focused on finding the number of ways to do X in a matrix, or path finding with minimal or maximal costs, or counting the number of something within a matrix. Another dead giveaway is when the problem directly gives us movement restrictions, like only moving left or right. The reason this pattern is so similar to the knapsack is because, generally speaking, the value you calculate at ij, a coordinate in the matrix, represents the most optimal solution to a subproblem up until that point. For example, this grid represents the number of unique paths this robot can take. As you can see, the numbers in this matrix incrementally build up from our starting point here, where the robot is, all the way to the bottom right, our endpoint. In this example, we calculate that the robot can take 15 unique paths to get from here to here. At any point in our matrix, we calculate the maximum amount of unique paths we can take to get to a particular cell. Like here, we have 2 ways, and here we have 3, and so on. Similar to the knapsack problems, we also use our previous calculations to incrementally build up to our final solution. So that's basically grid-based dynamic programming. Very similar to knapsack, except we're not optimizing for an external variable like capacity. In my experience, it's usually pretty obvious when you're faced with a knapsack problem, as you'll be given a scenario about optimizing for capacity and value, where grid-based problems only care about what's in the grid itself. But still, there are similarities between these two patterns, which is why I'd like to mention that none of these patterns are mutually exclusive. You can very well use some of the knowledge or techniques in the two-sequence pattern to help with the palindromic subsequence problems, or grid-based strategies with knapsack problems. The point of this video is to get you familiarized with various patterns and to give you a solid foundation to tackle more complex dynamic programming problems. I suppose before we move on, I should at least show you how we can move through this grid for this problem. So as you can see, we have ones calculated here and here, because if you want to get all the way over here, there's really only one way. You just have to go straight across. And same over here, you just go straight down. But when we come over here to 2, as you can see with these arrows that I've drawn right here, we can either go here and then down, or down and then right. So as you can visually see, there are 2 different ways to get here, assuming we can only move left or right, or up or down. And then similarly, if we look here at 3, we can get there by going right twice and then down 1, right once, down once, and then right again, or down once and then right twice. As we get out here, it's just going to take an extra step to get from here to here and here to here. Now, of course, there's more nuance to this problem, but basically you can see how in this entire grid we are incrementally building up to this final solution based off past information. So hopefully that makes sense. All right, Now let's take a look at the interval dynamic programming pattern. Interval refers to the fact that the problem can be broken down into smaller sequences or subarrays. We're usually given input in the form of an array or string, sometimes a matrix, but problems like these are usually linear. And basically, we can create subsequences by removing values at a certain index, which breaks the problem down into smaller arrays, strings, etc. One definition of subsequence that I really like is from the problem longest palindromic subsequence, LeetCode number 516, which defines subsequence as a subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. An example of this is with the coin game problem. The problem states that there are two players playing a game by removing coins from either end of a row of coins. Each coin has a value associated with it. Players take turns removing one coin from either end of the row until no more coins are left. The player with the maximum total value of coins wins. Given an array of coin values, determine the maximum total value that the first player can win. So basically, if we start with a list of coins, like we have here, 3, 9, 1, 2, and I start by taking a coin. I have two choices, either the 3 on this end or the 2 on the other. I cannot take from inside the array, only on the ends. Because I have two choices to make, we can branch off into a decision tree. If I take 3, then we're left with a subarray of 9, 1, 2. On the other hand, if I take 2, then we're left with 3, 9, 1. Then player 2 gets to make their choice, and the process repeats. If player 2 decides to take 9, then we have 1 and 2. Or if they take 2, then we're left with 9 and 1. Then we can further break down the subtree like so. I'm not going to finish the whole decision tree because it's going to take up a lot of space, but hopefully just based off this, you can get a pretty good idea of how we break down the coin game problem. So hopefully you can see how this pattern got the name interval, because at each level of the decision tree, we are creating a new subsequence based on the choices we make. Because again, let's say we pick 3, so that leaves us with 9, 1, 2. Then let's say the other player decides to pick 9, then that leaves us with 1, 2. Then let's say the other player again decides to pick 1, so then we're left with 2, which then finally gets picked because there's no other choice, and then we're left with an empty list. Or if we backtrack a little bit, if the player decides to take 2 instead, then we're left with 1, and then eventually nothing. And then a similar process repeats on this subtree. And as it turns out, the optimal solution we can make is to pick 2 first, leaving the other player to choose between 3 and 1. Afterwards, no matter which choice they make, we are free to take 9, which nets us a total of 11 is our max value. So how do you know when you're faced with an interval problem? Some things to look out for are keywords and phrases that suggest partitioning, subarrays, or subsequences. Basically, if you have to deal with subsequences in some capacity, and the goal is to find either the maximum or minimum value we can create or optimal game strategy, then you're likely dealing with an interval-based dynamic programming problem. And to round out this section, here are some problems that leverage this pattern. We have bursting balloons, longest increasing subsequence, and palindrome partitioning, to name a few. Alright, now let's move on to the recursive numbers pattern. So, recursive numbers is a blanket term used for various problems like Fibonacci numbers, house robber, climbing stairs, and many more. The reason for the name is because the solution to a given instance depends on the solutions to smaller instances of the same problem. The most notable example is Fibonacci numbers. If we look at this graphic, we can see that in order to calculate this Fibonacci number, we have to add up the previous 2. And the same goes for the rest of the numbers in this list. I actually cover this more in depth in the first dynamic programming video in this series, but in any case, the recurrence relation usually looks something like this. So if we want to find the fib of n, then we first need to calculate the fib of n minus 1 plus the fib of n minus 2. Most recursive number type problems share a similar recurrence relation. To understand why dynamic programming works really well for these types of problems, we can start with a naive solution. If we want to calculate the fib of, let's say 5, we first have to calculate fib of 4 and 3. So we can actually draw out a decision tree for this. So again, if we want to calculate the fib of 5, we have to calculate the fib of 4 and the fib of 3. Afterwards, branching off from here, we have to solve the fib of 3 and the fib of 2. And then the fib of 2 and the fib of 1 over here. And of course, this isn't the whole decision tree. We have subtrees over here, and so on and so forth. Basically, we solve a bunch of subproblems and perform repeat work, as you can see in our tree, which are the basics for applying dynamic programming to a problem. These types of problems also work really well with bottoms-up dynamic programming, which we covered in the last video. Since most of these problems use a 1D array, the logic is pretty linear. We don't need to create extra space to solve the problem. We only need to consider the past subproblems. In the case of the Fibonacci number problem, we only need the last two numbers. So drawing out our Fibonacci array again. So say we start with 0 and 1. That's all we need to incrementally build up to our final answer. Because we have 0 plus 1, which gives us 1, and then 1 plus 1, which gives us 2, and then 1 plus 2, which gives us 3, and then 2 plus 3, which gives us 5. Again, I covered bottoms up more in depth in my last video. If you want to learn more, then check that out. So that's a basic overview of recursive numbers. Now let's take a look at the palindromic subsequence pattern. The palindromic subsequence pattern revolves around finding or counting palindromic subsequences within a given sequence or string. If you don't know what a palindrome is, it's when a sequence of characters reads the same forward as backwards. For example, we have the word rotator here, which is a palindrome. Now you might be thinking, how exactly does dynamic programming help us here? Well, let's first run through a naive approach to check if this string is indeed a palindrome. We could start by repeatedly checking whether each substring is a palindrome by comparing characters from both ends. While this works, the problem is we'd have to traverse the entire array just to confirm whether it's a palindrome or not. Let's say we want to add s to the end of this string. Then we'd have to explore the entire string all over again to determine if it's a palindrome. So this naive approach has us doing a lot of repeat work. So how can we do better? Well, instead of looking at the entire string as a whole, what if we only looked at one character and expanded outward? Think about it. If we took the character A by itself, this is still technically a palindrome, because A read forward is the same as it is backwards. Now let's expand the string outward. If we want to check if this substring tat is a palindrome, we don't need to check if A is a palindrome again, since we already know it is one on its own. Now it basically boils down to checking if the newly added left and right characters are the same, which they are in this case. And the beauty of this is we can do this check in O of one time. It doesn't matter how big the string is either, because if we're to do this again, we only need to compare the left and right characters that we're adding. I should mention that this logic changes a little if we're working with even length palindromes, because the way we're doing it now won't work on a palindrome like Hannah. We'd have to start with two characters instead. In this case, we would check if n and n are equal to each other. They are, so we can expand outward like before. One last thing I want to mention is that these palindrome problems usually use a matrix to calculate their subproblems, so something to keep in mind. Before we look at the final pattern in this video, let's cover some notable problems that make use of this pattern. These problems include longest palindromic subsequence, count palindromic subsequences, and palindromic substrings. Of course there are more, but generally speaking, most problems that make use of the palindromic subsequence pattern have palindrome or palindromic in their names. Alright, and the final pattern I wanted to cover for this video is the two sequences pattern. Some popular problems that fit into this pattern are longest common subsequence, longest increasing subsequence, distinct subsequence, and edit distance, to name a few. The two sequences dynamic programming pattern revolves around solving problems that involve two linear sequences, such as two arrays or strings. The primary objective is to compute values that relate to both sequences. This usually involves trying to find subsequences in both of the input strings to perform a comparison or something similar. The classic example of a two-sequence problem is the longest common subsequence. As the name suggests, we're given two strings and we're tasked with finding the longest common subsequence shared between the two strings. For example, if we have a string ABCDE and another ACE, the longest common subsequence between the two would be 3, because we have a subsequence in the first string that spells out ACE, A-C-E, for a total length of 3. As you can see, the order of the characters in the subsequence is preserved, and this is important to understand, because if ACE was AEC, then the longest common subsequence would be 2 instead. So how does dynamic programming help for a problem like this? Let's go through the example a bit. If we compare the first character in each string, we know that they are both the same, so this is a valid subsequence. Since it's only one character right now, our longest common subsequence is 1. Because we know that the first character in both strings are the same, we can exclude it as we look through the remaining portion of the strings. So because we determined these are valid subsequences, let's just pretend like they don't exist for now. So let me just mark them out. So same as before, we compare the first character of each substring. Because B and C are not the same, that's going to break off into another subproblem. So now we branch off into two decisions. We can either take the B from BCDE or take the C from CE. So our decisions will look like this. Remember, as we remove characters from either string, as long as the order of the characters is preserved, then it's still a valid subsequence. In any case, as you can see with the subsequences here, the first characters are now matching. And basically the way we get this is if we choose to take B, essentially removing it from the substring, we create a separate set of substrings to compare. So then we'll have CDE with CE. However, in this case, if we choose to leave B alone and take the C out of here, then we'll end up with BCDE, but then we'll just have E here because we removed C from this substring. Again, since the first character in both of these substrings is now C, they are now matching, which means our longest common subsequence up to this point is 2. And we basically repeat this process until we've calculated the longest common subsequence between the two strings. Now, I won't fill out the whole decision tree because it gets very large, but if we follow the example, this will eventually break down the strings until we have E and E remaining. And since these will be our last matching characters, it will bring our common subsequence to a length of 3. So that's a general overview of how that would work. Now let's take a look at the dimensions for this problem. Since we have two strings that we're comparing and checking against one another, we can just multiply the length of both of our strings to get our dimensions, which means we'll be using a matrix. As you can see, this is a two-dimensional dynamic programming problem. The general idea is to compare the positions of characters between each string. So looking at our matrix, you can see we have an initial row and column of zeros. This is because if we were to consider ABCDE or ACE by themselves, then of course the longest common subsequence would be 0 since we're not comparing it to anything. Now, just a disclaimer, this might not always be necessary to include in your problem, but I figured I'd include it anyways. As we move deeper, you can see how we have 1 right here. This is because the first letter of both of these strings match. So the longest common subsequence up to this point is 1. The rest of the row here has 1s as well. If it helps, you can think of the A from ACE being compared to the entirety of the first string, like ABCDE or BCDE, CDE, and so on. As we move on, you can see how whenever two characters match, like the C's here, we increase the longest length so far. We do this by simply looking up to the previous calculation and adding 1 to it for a total of 2. Again, for this coordinate within our matrix, we're essentially comparing the substrings CDE and CE, which, if you remember, we included in our decision tree. Since we already know that C is our second matching character, that is how we get 2 here. This logic repeats until I reach the end for a total of 3. The final answer will always be in the bottom right of our matrix, as this is the area where the optimal solutions to all the various subproblems converge into the final solution. So hopefully all that makes sense. So that's going to do it for this video. These are all the patterns I wanted to cover, and I hope you found this video helpful. If you did, please like and subscribe, it really helps the channel. I'm also working on creating explainer videos for all of the Blind 75 problems. Here's a playlist if you're interested. If you find any more problems on LeetCode that you think would fall under any of these categories, feel free to mention them in the comments below. I'm sure many people would find that helpful. Thanks for watching, and I'll see you again soon.